Good morning, everyone. My name is Joe Marks. I'm a principal engineer working for EMR in Athena, and I'm here today to talk to you about turbocharging your query execution on EMR. So what are we going to learn today? We're going to learn 5 different pillars. First, we're going to start with our performance philosophy, which is why are we doing this, and how we formed a dedicated team within the organization to focus on just performance of multiple different open source engines, including Spark and Presto. Second, we're going to talk about our general focus areas, which is where we apply that effort and that focused, concerted team. Third, we're going to talk about the optimization techniques, how do we improve the performance of these open source engines? And then we're going to look at how those techniques that we used translate into real results for you, the customer, when you run your workloads. And finally, while everything that I will be focused on today is about engine, we do want to touch on beyond the query engine and additional features of Amazon EMR that allow you to get the most out of your hardware. So first, our philosophy. We essentially have 3 pillars. We want it to be the cheapest platform. We want it to be the easiest to use platform out of the box. And we always want to stay open source compatible. So what this means is that if you take your open source job, your open source Spark job or your open source Presto job, and you migrate that over to EMR, it's still going to work. So we strive for binary compatibility. And what we're trying to do is lower the barrier to entry such that you don't have to configure as many things, and it just runs faster, and that's how you get those cost savings. And we do this along 3 different dimensions. The first is configuration. What we strive for is improved out-of-the-box configurations for every single release that we have. So as you go from a release last month to this month to next month into next year, every single time you upgrade, you're going to get better default configurations. And this allows you to just upgrade without having to tune and configure your job. We're trying to do that for you out of the box. You still have the ability to configure your job beyond that. What we're trying to do is provide you the best out-of-box experience. Second is stuff that you don't really have access to as a developer, which is inside of the engine itself. So from a planning and an optimization perspective, we want to make sure that your job is going to run as efficiently as possible because we're generating the best logically optimized plans and then executing against them. And then third is the query execution itself, where even if we have the best plan, if any single operator within that plan is slow, then you're not going to get the best performance. And so we also focus on, even if we had ideal plans for every single query that's executed, how can we take individual operators that may be running slow and improve them? And so we'll talk about various optimization techniques, and we'll sort of dive into the details of different initiatives that we've done over the last 2 years towards this end. The first question we ask ourselves is, how do we pull less data? So obviously, if you're pulling a lot of data onto the cluster, you have to compute over a lot of data. So one large question we ask ourselves as a philosophy is, what are the various techniques that we can use to just not even get the data onto cluster? Because if we can avoid scanning the data somehow, then the rest of the query will run faster because it has less bytes to compute over. And so the analog for you would be something like, oh, I could model my data differently. I can use smaller tables. I can bifurcate, trifurcate something up front. But we don't want you to have to do that. And you can even use things like, maybe I was using an inefficient sort of verbose JSON file format, and you want to move to something that's more efficient, like Parquet or Orc. That's also possible. But we want to focus on, as a concerted performance team, the things that you wouldn't be able to do. So for instance, we want to optimize all fetches to your catalog. Instead of it being very chatty, we look for sort of particular opportunities where we're taking lots of round trips back and forth between the query planner and the catalog to look up partitions or dereference partitions or list the certain objects in your remote file store. So we just look for inefficiencies there. One particular one would be redundant scans. So within the planner itself, if we realize that you are maybe, say, scanning from the same table 2, 3, 4 times, we might be able to reduce that logically by saying we can do a single scan and then just filter those bytes differently into 4 different, or 2 or 3 or 4 different subsegments. But particularly, dynamic partition pruning is where things excel. So if you think about a predicate like, I'm filtering on partition key A, or partition key in A, B, C, D, E, most of the open source engines will look at that and say, well, that's a static predicate. I can filter that out because I can interrogate my catalog, look at exactly the partitions, partition A or B or C or D, and only prune and prune out everything else that's not those. But what they're not typically good at is taking a dynamic expression. So something like partition key is in a subquery that is sort of complex, or that scans from another table, or that joins some other data set. So one of the primary things that we do is we look at all opportunities where you're filtering on a partition key, and we ask ourselves, can we sort of pre-execute some of those subqueries or some of those other parts of the query to be able to even get a large set of those keys back, but still be able to filter those keys against catalog such that we don't have to touch the data in your remote file store. And a twist on that would be, even if we have to pull it onto cluster because it's not a partition key in catalog, we might be able to shuffle less data by taking a non-partition key. So we take that same technique that I just told you about in terms of being dynamic and knowing how to filter out certain data. If we can't filter it off cluster, then we're going to filter it on cluster as soon as possible. So intelligent filtering is basically taking the concept of dynamic partition pruning and applying it to non-partition keys. Beyond that, like you might, as a customer, say, I can bucket my data. Maybe you have table A bucketed 32 ways, table B bucketed 64 ways. As long as it's some sort of power of 2 offset, it's going to work, and you're going to be able to do map side joins. But that doesn't work for the wide variety of use cases. So if you have those same tables and you need to join them on different keys, right, you sort of have to bucket in one particular way. You're going to hash on a certain key or set of keys. And so you'd have to copy your data over and over and over again to have different hashing strategies and then select that dynamically at runtime. What we do instead is, instead of forcing you to do data bucketing, we say, what can we learn about the query at runtime? We try to take as much information as we know as possible to either rewrite or replan your query to run faster. So for instance, once you do an initial scan of data onto the cluster, you basically have full purview into the nature of that data, into the shape of that data, into the cardinality of that data. You can compute stats about it, min, max, histograms. And so we can take that information and we can actually rewrite joins to say, you know what, while at plan time, I wasn't able to take a broadcast join, which is a lot more efficient than a sort merge join, I can do it because the resultant after the filtering is so small that it now fits within the broadcast threshold. And so without statistics, and like this is a theme that you'll see throughout the rest of the talk, EMR is trying to do as many things as possible without stats. And so this goes back to our philosophy in terms of ease of use. We don't want you to have to say, I'm going to recompute stats on a periodic basis, or I'm going to rewrite all of my jobs such that when they touch my catalog and insert new data, they're going to always insert it with accurate stats, because our general philosophy is that stats are great, and if you have them, we're going to use them. But if you don't have them, because you either don't compute them or they're computed sort of with a trailing semantic where they're sort of stale, we want to be able to do as much as possible without stats. So this is all about having great out-of-box experience, and that's why we have several initiatives on our side for computing things without stats, and broadcast join is just one of them. Join reordering is another. So if you have a query that says table A, join B, join C, join D, if you join it in that particular order, it may perform well, or it might not, right? There might be a different order that performs better. Like maybe you should join tables A and B together, and then separately C and D together, and then join the results of that. So essentially what we do is, using the same scan data that we have, once we scan those bytes onto the cluster, we know more than what we knew at plan time. And so we will replan that and do joins in different orders based on as much information as possible. And so if we take all these things together, intelligent filtering, broadcast join without stats, join reordering without stats, this is how we can shuffle less data onto the cluster, or shuffle it more efficiently. A third optimization technique that we have is we ask ourselves, how can we start queries faster? So certain queries, if they run 1 hour, 2 hours, 5 hours, start time isn't really a concern. But increasingly, what we're seeing is different segments for queries that arrive on EMR clusters. We'll have short-running queries, maybe 5-second queries, 10-second queries. And so if you're taking a 5 or 10-second overhead, that doesn't really give you good responsiveness. So one pillar of what the team focuses on is how do we have good performance, not just for the long-running queries, but also the medium-running queries and the short-running queries. So we ask ourselves the question, how do we start queries faster? And one technique would be, I simply keep my application on all the time. So for instance, I can keep my Spark executors on all the time. But we don't do that in EMR because we believe that customers get a lot out of Spark, but then they also get a lot out of Presto, and they get a lot out of Flink, and they get a lot out of Hadoop and Hive. And so if you're this heterogeneous environment where you may have multiple open source engines that you use simultaneously, we don't want any single engine to be greedy with the resources that are available on cluster. So this is what we do. We try to start these applications as fast as possible, acquire the resources that those applications need, and then as soon as they're done with it, we return it back to the generalized pool to be used for some other application, either within the same engine like Spark, or maybe from a different engine like Hive or Hadoop. So one technique that we use here is parallel and async init. If you look at the processes that are required to, say, start a Spark executor, it goes through step 1, 2, 3, 4, 5. But by analyzing the actual startup process, we realize that most of these are not critical to the execution of most jobs. So what we did was we found a critical path. Those are still the ones that we init eagerly. But for most things, we can actually initialize it asynchronously in the background. Now, if later your job ends up needing one of these components, it'll get that component. And if the component is already loaded, then great. We just save the entire start time of that component. But if it's not yet loaded, then we're still going to block waiting for the completion of the load of that component. But these are just some of the things that we're doing to help your apps start faster. Another thing we do is, because we're instrumenting at the planning phase quite a bit, we understand stuff even before the execution of the query starts. So for instance, as we start to scan catalog and we get lists of partitions, and as we dereference each partition and start to get lists of files from the remote object store, we already know that we're going to have a minimal amount of work that we have to compute over. Well, we can take that minimal amount of work and start talking to the cluster to say, give me executors or give me workers ahead of time. This ahead of time fetch, doesn't have to block on the completion of the planning phase. So if planning is taking seconds or dozens of seconds, we can now have workers that are available in the cluster, such that the moment planning is complete, and then we sort of unleash all the work on those workers are already loaded. And even if the workers are still loading, they're now loading with parallel async init. Right? So even as we are starting them faster, we're now starting them in background as soon as we need. And then the third is really, how do we decouple the compute that we have from the storage that we're trying to pull from? So if you look at some of the open source applications, they typically have a one-to-one correspondence between a unit of work within that engine and a unit of fetch to that remote object store. So if I have one thread that's doing compute, I have that same thread that's going to sort of context switch back and forth between reading and then computing over what I just read, reading and then computing over what I just read. This works well, but it now bounds the amount of threads that you have to basically how many CPU cores that you have. And that's not really what we wanted to do. So what we ended up doing was we decoupled these in the engines that we offer, where we can now scale the number of units of work relative to cores, like some factor against cores. It's a 1x factor, 1.5x factor, 2x factor. But then we can scale the number of threads that we get to the remote object store much, much higher, because that's typically not a CPU-intensive operation and will scale out. And we hope to saturate the NIC faster and pull down data faster, such that those CPUs can remain busy all the time. These are just some of the things that we do to start your queries faster. In fact, we went so far with this data prefetch strategy that by the time the units of work even lands on the cluster, we've already pulled down this data. So similar to eager worker allocation, because at planning phase, we know the objects that we are going to pull down, right? We're doing list against that remote object store. We know the objects that we want to pull down. We can start instructing different nodes in the cluster to download that data and keep it in a shared thread-safe cache. Then once the unit of work actually lands on that same node and says, let me go fetch that object, the object is already there. So we kind of took the same concept as operating system, page prefetching, like other prefetching techniques, and just applied it to the space of big data, where we can pull down data even before the unit of work arrives on that node in the cluster. And then finally, the fourth is, even if we pull less data onto the cluster, or even if we shuffle less data around the cluster, even if we can start queries faster, how do we run them faster? So this is arguably the most important and where we do spend a lot of time. The first is just operator optimization. So if you look at a primitive operation, if you look at the efficiency of a certain join, or the efficiency of a certain aggregator, or the efficiency of even a built-in function or custom functions, we look for inefficiencies in that. So maybe if you're doing operation a scalar operation A into scalar B into scalar C, you may be doing a lot of redundant checks behind the scenes. So the way a lot of these operators are written is that they operate not knowing the safety of data that's arriving to them. So they're pessimistic. They may do redundant null checks across multiple operators. So we can realize this and actually eliminate all the redundant checks that when you're doing these things in tandem, if you're doing A into B into C, you don't need to do certain checks over and over again. And aside from that, we just look for ways to improve the performance of them. So we may even make some algorithms parallel, where they were previously doing a serialized execution. I want to skip over AQE for a second and go to stats inference. So because we have information about the execution graph of your job, like at planning phase, we try to make the best possible decision at plan time. But we can actually make a better decision than that because we can infer what the stats would be for downstream stages of the job. So for instance, if we have an operator that is strictly restrictive, given an n number of input rows, it's always going to be less than n output rows. We can use that information to inform part of the downstream plan to basically take a different path than it would otherwise. So now in terms of logically optimized plans, even before they're converted to physical, we can use this information and infer something about the nature of that operator to even construct better plans to begin with. But the reason why I skipped over adaptive query execution is because this is really the future. Like this is what we already started with 2 years ago when we said we can do broadcast joins without stats and we can do join reordering without stats. Like this whole notion of what information can we use at runtime to take a better path within that query plan is the very nature of adaptive query execution. So this is just the most generalized form of that. And aside from the two that I mentioned earlier, we can look at a plan, take a look at the output, every single intermediate output of that job. We'd look at the actual stats of that, and we may take a different plan, up to and including even changing join types. And so these are really the four different pillars. How do we scan less data? How do we shuffle less data if it does arrive in cluster? Can we optimize for short-running jobs and have a good responsiveness? And then multiple different techniques for just making all queries faster, despite if they're short-running or long-running or anything in between. And so now let's look at how all this converts into real results. So we have benchmarking. Now, one way of looking at benchmarking is how a lot of other industry vendors do it, saying, I have performance up to 18x better, up to 42x better. That's all well and good. And so we show you this graph, which is the theoretical performance that you can get. And you can see that because we have this concerted effort with this team, we're improving at every single EMR release that we do. And if you just look at the top 1%, that would essentially be equivalent to up to 18x or up to 42x that you'll see in a lot of marketing speak. But that's not actually how your jobs are going to run in practice. So what we wanted to do is be more comprehensive with our benchmarking results. We wanted to say, well, what could your top 5% be, top 10%, top 20%? So this is like a good graph for seeing what is the theoretical performance improvement that you can get when you apply all the optimizations that we've done. But really what we tell customers is a better way of looking at this data are average improvement factors. So think of things like a geometric mean. So if you take your short-running queries and your long-running queries and everything in between, you average them all together geometrically, what is the average improvement that I expect on a per-job basis? And we're looking at, for some of the most recent EMR releases, a little over 3x, maybe 3.5x. And then for the total sum hours, that's if you have disproportionately larger long-running jobs. Because we're improving long-running jobs, you can reduce the total sum. And so what we're seeing is over a sufficiently diverse set of workloads, we're actually getting a little bit better than 3x. Like that's closer to that 3.5x range. And we've done the same thing for Presto, right? We took all the good stuff that we were already doing on Spark and we said, yeah, we could probably apply most of these same techniques to a different open source engine and get hopefully similar results. Well, surprisingly, we got much better results. And this is like key to realizing that we can take different strategies based on the information that we have. So for instance, if you can reorder tables without stats because you can look at your remote object store and do list operations, and you can get header information, and you understand the general shape of that data, how many records, and the estimated number of records, and how many files that you're going to scan over, you can reorder those joins and you get really, really impressive results like 200, 300, 400x results. But again, that's only the top one, and that doesn't really tell the whole story. A better story is still these average numbers that I've been speaking about. So you get 1.5x improvement, 2.5x improvement. That's geometric means. That's if you take an average query runtime. But even our sums are really impressive because for Presto, it sort of skews towards the longest running queries, the worst performing queries before, perform much, much better with all this sort of dynamic reordering of tables and using, approaching it from a statless plan perspective. And so that's everything about engines. You can see that the performance of Spark and Presto are improving measurably, and we're going to continue to do this. So every single time we release, we're doing more and more. And so, one of the philosophies here should be, if you can afford it, upgrade early and often, and you're going to get these performance benefits, which for you results in lower costs, which is one of our original pillars. But let's also talk about, in our remaining time, some considerations that you would have beyond the engine. So even if the engine is completely optimal, it doesn't necessarily mean that you should keep it just to a C5 or just to an M5. So we also want people to think about hardware too. So AWS offers the Graviton 2 platform. And what we did here was we ran a benchmark to say, what if we took the existing workloads that we have and just shifted them from a C5 to a C6G, or from an M5 to an M6G, or from an R5 to an R6G. When we do that, we get performance improvements essentially for free. This is the exact same cluster configuration, same number of nodes, same relative size. We're just upgrading to Graviton 2. Same Spark configuration, same yarn configuration, same Presto configuration. You get performance benefits because it just executes the code faster. It's the exact same code. It just executes it faster. And so again, this is one way of viewing it. You can say up to a certain percentage benefit. So we can say, yeah, we can up to 50%. But a better way of looking at this is ranges. So how's this improving with each of the families? You can see that essentially C's, M's, and R's are all improving from a price performance ratio. So if you were to essentially merge the two sets of graphs that I had before, if you take the raw Spark and Presto improvements, and then you take the runtime improvements just from upgrading hardware, you can see where you might be if you're on older versions of Spark and upgrade, and older versions of Presto and upgrade, and start using Graviton 2. Aside from Graviton, there's also certain features that we offer within the service. So EMR has a feature called managed scaling, which we released this year. And managed scaling is essentially trying to right-size the cluster to the workloads that are arriving on it. And so historically, even if you had used the auto-scaling feature, you would have had to choose, when am I going to scale up? When am I going to scale down? What are the metrics of concern for me? What are the thresholds of concern? How many metrics do I want to use in combination to scale up and to scale down? How long do I want to wait for my cooldown period? When I scale up, how many nodes do I want to scale up? Or how many nodes do I want to scale down? So all of this was very powerful because it was configurable by the user, but it was also very complex for that reason. And so unless you were very, very familiar with these workloads, you might not make the best decision. And so what we said was, can we simplify this experience for the customer? Can we make it more of a known-brainer? This goes back to our ease of use pillar right at the start of this talk, where we want the out-of-the-box configuration to work for you really well, and we just want you to save money by using EMR. And so managed scaling is something that we implemented. Essentially what it says is, we are going to internally track all the fine-grained metrics that are coming out of your cluster. And we do this every couple seconds. We're going to send that information up to the service, and then we're going to analyze that. Based on the back pressure that we see of jobs building up, or how many pending work items are not yet currently being worked on, how much do we have to scale up? Or if that is now cleared, how much do we have to scale down? And so we can take that action arbitrarily fast. We do buffer it up to in like 1 minute buffers right now. But we can take very fast action to be able to move to exactly the number of nodes that we think is required to run your workload. So whereas before you had to choose, do I want to scale 5 nodes up at a time, 10 nodes up at a time? sometimes 5 would be good, and sometimes it would be massively underscaled. And so you choose, maybe I want to step up 20 nodes at a time. And 20 nodes is good for your large jobs, but now it's not good for your small jobs. So like there's really no good number unless you just move to directly what you think that you need. And that's what we've implemented in terms of managed scaling. We essentially take all of these metrics and compute the number of nodes that we think that you currently need in order to run that workload best, and grind through it and meet the maximum number of SLAs possible. And then 1 minute later, if we believe that information is now changed, we'll scale to some other metric. So we'll continue going up, 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 or down, 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 or anything in between. So you'll have this mixed mode where even with spiky workloads, it'll work pretty well. And so how does this also translate into benchmark results? So we did benchmarking here, and essentially our observations broke down into 3 different types of jobs. Jobs that were just strictly faster, but not necessarily more cost effective. Like these were jobs that you could use more nodes for a shorter period of time to bring in your job SLAs and compute the results faster, but you didn't necessarily save cost because the area under the curve would be the same. The other would be jobs that were just strictly cheaper, and there were a lot of these, because what you find is that on this previous graph, if you just had that sort of purple line at the top and you weren't scaling up and down the cluster, there's a lot of waste there. And so this whole second pillar is all about removing the waste. There was a huge number of jobs, even in a sufficiently diverse workload set. We ran about a dozen different permutations of jobs and arrival rates on clusters. What we found was that the most common thing is that you simply save money, because there's a lot of waste there, and you shouldn't be scaling your cluster to the high watermark always. And then the third is really sort of the idealized world, which is not only did it get faster, so you met more SLAs, but it also got cheaper. So faster and cheaper is sort of the ideal. We're not there yet for as many workloads as we would like, but we're sort of moving in the direction where we're taking all the metrics that we're emitting, and we're trying to figure out how that we can improve these algorithms to have more jobs fall into the faster and cheaper bucket. And so what are our key takeaways here? It's all the graphs show that every single time that EMR does a release, it gets faster. Whether you're using Spark or Presto, whether you're on AL1 or AL2, we have a concerted effort behind the scenes to make your jobs run faster. And so if you can afford it, we definitely see a lot of value in upgrading. So instead of, for instance, trying to tune your job to eke out a little bit more performance, to make it such that you can meet budget for the year, you can also meet budget by taking that same development effort that you would normally spend on optimizing your jobs and just upgrading. So sort of follow the compiler theory, where if you just recompile your code with a later compiler, it gets faster. We want you to upgrade and just rerun your job, and with a certain probability, it is going to get faster. Then, consider leveraging Graviton too. So even if you're on the C5s or the M5s, consider what would it take for you to attempt upgrading to see whether your jobs can run faster, because now we're talking about a price performance curve. You don't even have to retest your jobs on a new version of the open source software. You can use the same version of the open source software and just switch out the hardware underneath. And then if you really can, we encourage everyone to enable managed scaling and give it a try, because it's either going to make your jobs faster or cheaper or both. And there were very, very few workloads that we found didn't at least show some improvement. But what we found across the board was, even if it didn't show an improvement, it didn't regress. So it wasn't leading to cost increases. So we do believe that, strictly speaking, and for a sufficiently large workload, it's safe to turn on for that workload, and you should see some sort of benefit. So we're eager to hear your results with that. And thanks for your time today.